Video 3 on magnetism and induction. So there's certain factors that influence the strength of an electromagnet. Those factors are, well, the number of turns of wire. So how many times I turn that wire. Of course, that, if you were to straighten that wire out, it would be longer. And the more turns, the longer the wire. But the number of turns of the wire per unit length of the coil. So the greater the number of turns, the more turns, the greater the strength of the magnetic field. So the number of turns. Also, the higher the amount of current through the conductor. So the more current through that conductor and the more turns through that conductor is going to equal a stronger magnetic field. Also, the larger the cross-sectional area of the coil, so how large it is, and the type of material within the path of flux. A soft iron core will have more saturation. There will be less reluctance, more permeable, versus an air coil, which is the worst core. An air core, which is the worst core because flux lines don't want to set up within air. So, and in fact, they go out of their way. If you think back to the earlier video when I talked about induced magnetism, and we saw that the magnetic lines of flux actually go out of their way, further out of their way to set up in a highly permeable, low reluctant environment than do they through air, and they won't set up in an air coil well. So if the coil is permeable, soft iron with low reluctance, then we're going to have a stronger field. So it brings us to Fleming's left-hand rule for electromagnets. And Fleming's left-hand rule for electromagnets looks like this. So your thumb, as you can see here, the thumb is pointing in the direction here of the force or thrust. So I got my thumb here. And then this is the forefinger here. This is the forefinger. And then this is what we call the center finger. Center finger. And so when you're trying to identify either the direction of force or the direction of the magnetic field or the direction of the current, you can use this. And notice that this finger here, the center finger, is actually, if you are holding your palm out, so your palm is facing you, your thumb's pointing up, and your forefinger is pointing to the right like this, this finger should be pointing directly at you, directly at your face or at your chest. So notice that they're on different planes. This is on this plane versus your center finger is on that plane, so different planes. So that's very important to understand that, because the direction of current is not on the same plane as the direction of force. They're 90 degrees off from each other. So you can see that the thumb points to the direction of the induced force or thrust. So we say, well, thumb, thrust. The forefinger points in the direction of flux, F for forefinger, F for flux, and the center finger points in the direction of current. So C for current, C for center, and C for current flow. Now if we look at this, this is showing a magnet with the north and the south pole, and you can see how I've got the flux going from the north to the south pole. And what we're going to do is we're going to use the left-hand rule in order to determine the direction of the current flow. And we can see here that this is my thrust here, or direction of force here. So as you take this wire and you push it down through this magnet, it's going to cause a current to flow. And as you push it down, it's going to cause a current to flow in one direction. As you pull it back up through that magnet, that magnetic flux, it's going to cause a current to flow, but it's going to cause current flow in a different direction. So let's take a look at that. So as it says here, a voltage is induced when a conductor cuts magnetic lines of force. So let's take a look at this one. So the first one, I've got my thrust is going in this direction, so my thumb is going to be pointing down. My left hand thumb is going to be pointing down. Then what I'm going to do is I'm going to take my forefinger and I'm going to point it in the direction that the flux is moving. So in other words, this direction here. And then my center finger is going to be pointing actually in this direction. I draw it, but can't draw that. So if you take a look, in this case, if we were to look at this wire, if we're just right at this point here, we were to section this wire right here and look at it, we would actually see that the current is flowing away from us at this point. Like that. And if we were to determine the force as a result of that, my thumb pointing in the direction of force would be in this direction here. So now let's take a look. If I was to change this and say, okay, well, our wire is now inside here. It's in here. I've just pushed it down, and the key to this is that current will only flow in a wire when it's being moved through lines of flux. There is no current flowing in the wire if that wire or the flux is not moving. So my wire has been pushed. I have thrust it down this direction, and now I have no current flowing. Now I want to take that, and I'm going to move that wire up. So my thrust, my thumb, my thrust is going to be pointing in the upwards direction. My flux direction hasn't changed, so my flux is still in this direction, so my finger is pointing to the right, my thumb is pointing up, and then my center finger is going to be pointing towards me, in which case that current is coming towards me. Notice it's in the opposite direction as the other one. So as I push the wire down, I get current flowing in this direction, and as I push the wire back up, I get current flowing back in this direction again. So just looking at this section of wire, if I was just to cut that and look at the end, hold it up and look at the end of it, the current would be flowing towards me, and that induced magnetic field as a result of that, I'm going to place my thumb in the direction of current flow, so my thumb is pointing towards me, and then my fingers wrap around in this direction, so there's the induced magnetic field around that wire. So now we come to some example problems. So for electromagnets, the strength of the induced magnetic field is directly proportional to the number of turns and of wire and the amount of current in amps going through the wire. Therefore, we say that the magnetomotive force, MMF, or the force magnetic, which is more popular to call it the force magnetic, is equal to the number of turns times the amps. So the force magnetic equals amps times turns. Fairly simple. So, you know, we could say, okay, well, I could say force magnetic. I could put that here, and then I could put amps here and turns there. So if I look at this, the question here is, what is the MMF if a current of 5 amps is flowing through a coil of 100 turns? Well, if the force magnetic is equal to, and we're calling amps I, and we're calling number of turns N, so we can take a look at this. I'll make it a little bit bigger this time. So the force magnetic equals amps times number of turns. So if the amps are 5 and the number of turns are 500, then I have 500 amp turns. Let's look at question number 2. If the length of the coil is 0.1 meters, what is the magnetic field intensity in henries? That's a unit of amps per meter. So henries is equal to amps times number of turns divided by length. So the intensity in henries is equal to the amps times the turns divided by the length in meters. So I've got 5 times 100, and we're saying it's 0.1 meters, which gives me 5,000 amp turns per meter.